right, guys, as you can see, the sun's out today, so it's a good day to talk about the sun. So these are your notes for the sun. We're not going through all 30 slides, only 11, so it'll be short, sweet, to the point. So the sun. We know the sun is the closest star to Earth. That's where we get our light from every day, okay? Hopefully, unless it's cloudy. But that's where all that sunlight comes from that can help the plants make food, helps us with our vitamin D, all of that fun stuff. The sun is an average sized star. So if you think of a spectrum of stars, you have really little ones over here, really big ones over here, the sun's in the middle, okay? Now the sun isn't just a big ball of gas. There are definite layers to the sun. So if you look down here, just like with Earth, we're gonna start with the core, okay? And from the core, then we go to the radiation zone. From there, we go to the conventional zone. You notice the different colors. Okay, from there, we go to the chromosphere. And from there, we go to the photosphere. We've got supragranular cells here in the chromosphere. Okay, so make sure you know what you're looking at. Okay, you've got to be able to identify this stuff. So let's look at the next slide. So when you think sun, I want you to think how the sunlight gets to us. And how that gets to us is through radiation, which we know. And what radiates is a photon. Okay? That is a particle of light. Not a proton, a photon. Think photo, P-H-O. Okay? A photon carries the energy proportional to the radiation frequency, but it has zero mass, okay? Now, when you think of the sun's layers, I want you to think of the outer layer. That's the corona, okay? So the corona is the outermost layer of the sun. It's very dim. We can only see this if there is an eclipse going on, okay? So think back a year or so ago when the eclipse happened and you saw the dark circle, and then around it you had this smirkle of light. That's your corona. Okay? The chromosphere is next, and that's where the sunspots form. Okay? The photosphere. This and the above two layers, so those three layers, the corona, the chromosphere, the photosphere, they create the atmosphere we see. Okay? The photosphere is the layer we see every day. It's the easiest to spot. Okay, now if we get down out of the sun's atmosphere and we go to the convection zone, photons are moving in the convection cycle. So remember heat. Remember the convection cycle. It heats up, it rises, then it hits the top and it cools down and it goes back down. It's a circle, a cycle. Okay, it takes 170,000 years for a photon to reach the photosphere. Now, from the convection zone, we go down to the radiative zone. And that's where the photon moves from the core to this layer to the convection zone. So it's kind of a highway, think of. Those photons leave the core and they radiate out to go to the convection zone. Okay, in the core, that's where the gravity is so strong that it's bringing hydrogen together to initiate fusion. Okay, this is a big thing on how the sun operates, is knowing that core, the gravity is so strong pushing in on it, it's taking two atoms of hydrogen and pushing them together, okay? And that's fusion. So fusion, this was a vocab word, is when hydrogen burns or fuses together to form helium. So if you take one hydrogen atom with one hydrogen atom, which each have one proton each, one electron each, when you push them together, you all of a sudden get two protons and two electrons. So that two proton now has taken that hydrogen and made helium. Okay, here's the big thing you need to know with this. Hydrostatic equilibrium. That's when the gravity and the pressure on all sides are pushing against each other. Okay, this is what keeps the sun from flying apart. So when you look at the graphic, you have all that gravity pushing hydrogen and helium and everything in. Okay, then you have these free neutrons pushing out. So think the gravity's pushing in, and then the pressure from this chemical reaction is pushing out. That's hydrostatic equilibrium. Okay, the structure of the sun's corona is shaped by its magnetic field. So we talked about how the Earth has a magnetic field and magnets. The sun also has a magnetic field. Here's the difference though. It varies over time and from place to place on the sun. The sun's magnetic field can be very strong. You see that inside the sunspots. The magnetic field can be several thousand times the strength of the Earth's magnetic field. Okay, so let me go back one. The magnetic field can be thought of as lines that connect north and south polarities. Okay, the magnetic fields connect opposite polarities. We know this. North and south attract. Opposites attract. It's like a bad love song. Okay, however, on the sun, we observe bits of north and south polarities scattered all over the surface. So it's not just a north pole, a south pole. It's going to be multiple north and south poles that you're seeing. Okay, so energy slowly moves through the layers of the sun. Energy moves through the layers of the star by convection and radiation. Core, and then it radiates out of the radiation layer to the convection layer, okay? During convection, hot gases move up. Remember the convection cycle. We talked about it, how you can bake in a convection oven because that air heats up and rises, and then when it hits the top, it cools and comes back down. Okay, so with a star, which the sun is, hot gas moves upward and from the star's center, and then cooler gas will sink down towards the center. It's a constant cycle that's going on. And then during the radiation, think atoms absorb energy and transfer it to other atoms in random directions. It's radiating out. Okay? It's like you take a bucket of bouncy balls and you dump them at the same area. They're not all going to bounce in the same way. They're going to bounce out. Same with radiation. Okay, atoms near the star's surface will radiate energy out to space. Okay, we know some stars do appear brighter than others. It depends on the star's temperature and the distance from Earth. We're going to get more into that on Friday when we start talking about stars. Okay, we learn about stars by studying their energy. We can't send something to a star and have it, investigate for us, send us video and all that. So we know stars produce a full range of electromagnetic radiation. Okay, from high energy X-rays to low energy radio waves. And you should know that. That should be the mental picture in your head, is that electromagnetic spectrum. Okay? We know scientists are using optical telescopes to study the visible light and radio telescopes to study the radio waves. And then Earth's atmosphere blocks some of these waves, so telescopes in space can study a wider range of the spectrum. The whole point of Earth's atmosphere is to block out some of those harmful things, okay? So it's not letting everything in that we could see here from Earth. We've got to have some things out in space to see. Last one. A star's color is related to its temperature. Hotter objects glow with light that has shorter wavelengths, okay? So it's closer to the blue end of the spectrum. Cooler objects glow with light that has a longer wavelength, so it's closer to the red end of the spectrum. Okay, remember the Doppler effect in space? Red-blue shift. Okay, hot stars emit more energy at every wavelength than cooler stars do, which makes sense because we said heat is actually the measure of energy. So the higher the temperature, the higher the heat, the more energy it has. Okay, that's it for today on the sun. If you have any questions, feel free to get a hold of me.